All right, I've got problem 1 here for section 18.6. And basically this one is going to be a little bit more conceptual here, you'll see, but I'll show you. So we have an electric power utility forecasts that R sub t kilowatt hours of generating capacity will be needed during year T. The current year is year 1. Each year, the utility must decide how much generating capacity should be expanded. It costs C sub t of X dollars to increase generating capacity by X kilowatt hours during year T. It may be desirable to reduce capacity, so X need not be non-negative, meaning that it can be negative. During each year, 10% of the old generating capacity becomes obsolete. Underline that. 10% becomes obsolete and unusable. Capacity does not become obsolete during the first year operation. And it costs the utility MT of I dollars to maintain the I units of capacity during year T. And at the beginning of year 1, we know 100,000 kilowatt hours of generating capacity are available. Formulate a dynamic programming recursion that's going to enable the utility to minimize the total cost of meeting power requirements here for the next T years. So we don't have a set end here, we're just going to T years. And then I did forget to underline, year 1 we do have 100,000 kilowatt hours. So to start off, we're kind of looking at, we're dealing with F sub t of IT, and we're trying to minimize the cost here of C sub t of xt here. So that's going to be the cost each year with respect to the kilowatt hours needed for that year, plus m sub t of I sub t plus xt. So this is just going to be basically talking about the utility cost here to maintain the I units of capacity plus the amount of capacity that we're using with the kilowatt hours. And then we need to add on f of t plus 1 for the following years. And we know that since 10% of the old generating capacity becomes obsolete, it's going to be 0.9 of I sub t for the previous capacity plus x sub t. So starting with year 1, we have f sub 1, and we know that we have 100,000 to begin with here, because they gave us that in the problem. It's going to be the minimum of C sub t of, in this case it's going to be x1 plus m sub t, which actually these t's are all just going to be 1s, of 100,000 plus x1. And then for f of t plus 1, this is going to be f sub 2 here. And 0.9 times that 100,000 is just going to give us 90,000 plus x sub 1 here. And then carrying on this pattern into f sub 2, it's going to be f sub 2 of 90,000 plus x sub 1. And now we're trying to minimize C2 of x2 plus m sub 2 of 90,000 plus x1, which we find from up here. We have to add on that x2 to the end. And then now we're doing, for the t plus 1, it's going to be plus f sub 3 of 0.9 of 90,000 is going to be 81,000 plus 0.9 times x1 and then plus x2. And then this kind of just goes on, so forth until we get to however far t years we're going to be at, which is just going to keep fitting this exact structure here. So that's pretty much the solution to this problem. There isn't really a definitive answer because we're just dealing with t years here. Thanks.